Hello guys, in this video we are going to learn about counter operations. First we will see the count up counter. Later we will learn about the other counters such as the count down and count up and down. Finally we will use the counter operations in a practical project. Let's start with the count up counter. This is its ladder symbol. This instruction has some inputs and outputs. Like the timers, the counters need a data block to work properly. This instruction counts up by 1 when the value of the counter input CU changes from 0 to 1. Similar to the timers, here we have the reset and the preset value terminals. Suppose the present value is equal to 3. Let's see how the outputs change with this diagram. When we have a positive signal edge at the counter input, this will have a 1 in its count value or CV, and it will increment by 1. So with another positive signal edge, the counter value changes from 1 to 2. Finally, with the next pulse, the counter value reaches 3, which is equal to its preset value. At this moment, the output changes from 0 to 1. For this counter, when the counter value is equal to or greater than the preset value, the output will be on. After this moment, if we have another positive pulse, the output will remain on, but the counter value increments by 1. The counter continues its counting until a positive signal edge appears at its reset input. At this moment, the output goes off and the current value changes to 0. Now let's see this counter in the TIA. First, I insert a counter up instruction from the write list. Automatically, the TIA requests a data block for the counter. Here, we can define a name for the data block. Now let me define the counter input outputs to some addresses. I want to test this program with the SIM table. So I must delete this block which has been inserted to use the Factory IO. Now let's have a virtual PLC. Now let me create a SIM table. Remember that here we can select the PLC inputs. Now let's have a better view. Alright, as you can see, when I activate the I0.0 contact, the counter value increases until it reaches its preset value. At this moment, Q0.0 output will be on. After that, the output remains on and just the counter value increases. With the second input, I can reset the counter output to 0. Notice that the reset takes a priority over counting. So, to start the counter again, I need to deactivate its reset input. Now let me save this virtual PLC with its settings. I will use that for the next simulation. Let's click on this icon to go offline. The CTU is the syntax for the count-up counter. The next counter is the countdown counter, which is defined with this syntax, CTD. This counter is like the previous one, but it has a little difference in its inputs and it works reversely. It counts down from a preset value to 0. See this diagram. At first, the output is on. This counter has a load input instead of a reset 1. When the RLO at this input changes to a 1, the preset value loaded as the current value and the output will be off. Then, with each positive pulse at the counter input, the current value decreases by 1 unit until it reaches a 0. At this moment, the output changes to on or true. For this counter, the output will be on if the current value is equal to or less than 0. With the next pulses at the counter input, the current value decreases and the output remains on. When we have another positive pulse at the load input, it transfers the preset value to the current value and turns the output off. Like the previous counter here, if both inputs are activated, the load command takes priority over the counting. Alright, now let's experiment how this counter functions in the TIA. First, I insert a countdown counter to the previous program. Pay attention, here I have used MW0, which consists of bytes 0 and 1. So the next usable address of the memory is the MW2. Now let's save this program and compile it. As you can see, there isn't any error or warning. Now I need a virtual PLC to test my program. Let me open the virtual PLC and transfer my program to it. Let's change these inputs. Note that in the beginning, this output is on. When the load input is activated, this counter copies the preset value to the counter value. Then, with the next applying input pulses, I can decrease the counter value until it reaches a 0, which causes the PLC output to be on or true. With the next pulses, the output will remain on until the next positive pulse is applied at the load input. Pay attention, by default the integer format is selected for the numbers. It needs to be 2 bytes or 16 bits. It can store numbers from minus 32,768 to 32,767. Other formats can be selected as well. For example, a double integer needs 4 bytes. So I need to modify MW2 to MD2. Also, I can select unsigned integers. With this format, we can store numbers from 0 to 65,535 in 2 bytes. Let me go to the FBD language. As you can see, the ladder and FBD symbols of counters look alike or are the same. Let me test this program. When the current value reaches 0, the output will be on, similar to the previous test. But if we have another pulse at the counter input, the current value won't be negative, unlike the previous test. Because when the unsigned format is selected, the lowest number is 0. Now, after a short review, we will see how a count-up-done counter works. Then, we will do a simple project to see how counters can help us in an industrial process. Let's get into it. These are the ladder symbols and syntaxes of these two counters, the count-up and the count-down counters. We have seen how these counters work. By default, the format of their numbers is an integer. Let's open the TIA. For a counter, here I can change its number format. The main differences between these formats are their range and also the number of bits of memory that they use. Let me open the help window. Here search integer. By clicking here on the right side, we can see the integer formats. For example, click on this format. As you can see, the integer number needs 16 bits and it supports a number from minus 32,768 to 32,767. Another common format is double integer. This format needs 32 bits, which it equals 4 bytes. Naturally, its range is bigger than the integer format. We can see its structure at the bottom. For the double integer format, the bits 0 to 30 represents the number value and the bit 31 represents the number sign. 0 is used for positive numbers and 1 for negative numbers. Alright, when we combine these counters, we get the count up and down counter. As you can see, this counter has all inputs and outputs pins of the two other counters. Now let's see how this simple laddered program works. Each pulse at the CU input makes the counter value increase. For example, it starts from 0 to 3. At this moment, like a count-up counter, the QU output will be on since the current value is equal to the preset value. After that, if we have 3 positive pulses at the second input, then the current value decreases from 2 to 1 and finally to 0. Here, like the countdown counter, the second output will be on. The reset terminal can change the output CV to 0 and the load terminal or LD is used to copy the preset value onto the current value or CV. So this counter has three outputs. The first output will be on if the CV is equal to or greater than the preset value. Otherwise, it will be off. The second output, or QD, will be on if the CV is equal to or less than 0. And also, we can have the counter value using the CV output. Now, pause this video and exercise with this counter in TIA, like the previous counters. Then we are going to define a project using the Factory IO together. Here we have two conveyors which are called entry and buffer conveyors. Also here we have three sensors and two push buttons to start and stop the process. When some boxes are placed on the first conveyor, the PLC program moves on to the buffer conveyor, and then we can count them using these sensors. Pay attention, when there is not any box on the conveyor, these sensors send positive signals to a PLC until a box is placed in front of them. After the accumulation of three boxes, the buffer conveyor moves them. First, let me test the final project and then show you how we can generate it. Let's see what happens if I press the start push button. Now let me press the stop push button. This line will be a stop when the buffer conveyor moves all the boxes. Alright, now I am going to show you how I can design this plant in Factory IO. First, here, select the fourth project, QE of items. Then I need just to insert a control box with the start and stop push buttons. Now let me define the tags for my PLC input outputs. Here we have two push buttons to start and stop the process, three sensors that are connected to my PLC inputs, and also two conveyors which are controlled by the PLC outputs. Now let's start the programming steps. First, pause this video and try to do this project by yourself. You may use counter operands to write a simple program. Test it, and if there is any bug in your program, try to change it. Then you may compare your program with mine. I prefer to save the start-stop requests in a bit of the PLC memory, the way I did in previous project. In the third network, I want to write a program to count the number of boxes on the buffer conveyor. Let me explain my program. At the third network, I have used the countUp and down counter. I linked the CU and CD inputs to the two sensors which are installed at the first and the end of the buffer conveyor. Here I have used a bit of logic operand to detect positive signal edges at the first input. When a box is behind the sensor, it sends a 1 to the PLC. When a box is passing through this sensor, the sensor output signal changes to 0. And then if the box passes completely, we will have a positive signal edge, which makes the counter value increase by 1 unit. With the next boxes, the current value will be 2 and then 3, which is equal to the preset value. The first output of the counter QU will be on. In the same way, the second sensor makes the counter decrease its value from 3 to 0. At this time, the QD output will be on. Also, I have used the start push button to reset this counter at the starting moment. I expect you to write this program. Let's look at mine in the next network. Here I have used the SR flip-flop to turn on/off the first conveyor. It will be on if the start push button is pressed or there are not any boxes on the buffer conveyor. Pay attention, I don't want to turn on this conveyor when the stop memory is off. The entry conveyor will be off if the stop push button is pressed or we have 3 boxes on the buffer conveyor. All instructions in this network related to the bit logic operands, which we learned about them already. Just pay attention here to see how we can refer to the QU output of the counter. As you know, when this output is on, it means the current value is equal to or greater than the preset value. That means there are 3 boxes on the buffer conveyor. Well, let's come back to the TIA software. Here I just need to define my counter name and then select and use its input or output. Alright, let's see my last network program to turn on off the buffer conveyor. This network is like network 4. The buffer conveyor will be on if there are 3 boxes on this conveyor, and it will be off if there aren't. Also, if the first sensor detects a box, the conveyor must be on until this box is completely placed on the buffer conveyor. Now what is this contact for? Pay attention. We don't turn off this conveyor for the third box because all 3 boxes must be moved. Alright, this is the program which is tested already. Well, I have tested this program with the TIA simulator. Now let's test it using the PLC. Here we have 2 outputs that are linked to the 2 conveyors in Factory IO. Now let me press the stop push button. As you can see, the line will be stopped after moving all the remaining boxes on the second conveyor. In the next video, we will learn comparator operations. See you in the next video. Take care.